Cool. Thermochemistry. Let's talk about enthalpy. First off, what do you guys remember about enthalpy? Enthalpy. You wouldn't know anything about enthalpy. You didn't take level 2 chemistry. Remember endothermic, exothermic? What does enthalpy mean? Change, good. There's a type of energy. What energy are we thinking about? Oh, so close. It's heat. Heat. I want you to go to one of the physics teachers we have, and you tell them that kinetic energy and heat energy are the same thing, and you see how that goes down. Actually, who's taking physics right now? Is it the same thing, Emma? No, didn't think so. Heat energy is talking about temperature. I would say it's similar. Heat energy is talking about temperature. Kinetic energy is talking about movement. But to be fair, the hotter an object is, the more it's going to vibrate and move. So I can see Klein's point, but I wouldn't call them the same. Okay. Heat energy. So we remember the words endothermic, and we remember the words exothermic. What does endothermic mean? Yeah, requires energy. Another way to think about it is absorbs energy. So this one's absorbing energy. And then exothermic would release it. To help you guys kind of tell the difference between the two, endothermic reactions often feel cold to the touch. And that's not because, so this is, I love this as like a fun fact. We don't actually feel cold. So like when I touch something that's cold, I'm not feeling cold. I'm losing heat, and that's why it feels cold. Should I start over? Feeling cold is not something that is like, you don't like get cold being hit with you. The sensation of cold is the result of the loss of heat. So because I've touched something and I'm losing heat to that object, I feel cold. So there's no such thing as cold, if that makes sense. So this one feels cold. Exothermic then, opposite, feels hot. Yeah, let me just pause the recording.
Any students and five students.
Cool. All right, the other thing we need to think about as a nice little reminder, because it's going to come up in thermochemistry, is the phase changes and how does that relate to enthalpy. So we know that endothermic absorbs the heat energy, exothermic releases the heat energy. Ooh, now I remember. The other thing we need to think about when we're thinking about whether or not a reaction is endothermic or exothermic is comparing the energy of the reactants and the products. So I have reactants, and then I have my arrow, and I have products. Now, when I have my reactants, I need to break the bonds of my chemical or my compound. And then when I make my new products, I make new bonds. So this one here, we have to break the bonds. This one here, we have to make bonds. Yes. If I break bonds, do you think that's going to require energy or is it going to release energy? Breaking the bond. It is required. So we're going to need energy to break the bonds because they don't want to be broken apart. They're nice and stable if they're in their bonds. So that one needs energy. So if we're thinking about the flip side, what happens when I make bonds? Release the energy. Sorry, lost the focus. There we go. All right. So one of the things that we can compare them when we're thinking about endothermic reaction versus exothermic reaction is how much energy is stored in that chemical compound. So if my chemical compound, if the reactants have more stored energy than the products, so this is stored energy, reactants have more stored energy than the products, what that means is that the energy was released and that makes it an exothermic reaction. You guys would have often seen this as a little graph diagram with the, like, I'm sorry, that's a bad drawing. You would have seen this as an energy diagram with the reactants up here, and then a reaction occurs, and then you have your products, and then that energy release is the difference. Yeah? And if I did the opposite, my products had more energy, then energy would have been absorbed. Which is endothermic. So if I was to draw that diagram, it would be products. Am I doing it the wrong way? I keep doing it wrong. It would be reactants and then absorption of energy in my products. If I was to do a quick little diagram to show what it's supposed to look like, just in case it pops up again. This is basically a recap from last year. Are we okay so far? All right. Let's think about the phase changes, because this will definitely come in this year, and you'll see in the practice question that I have given you guys when we go through the notes what I mean. So we have solid, liquid, and gas. And it could also go backwards too, because you know we can freeze things. So yeah, solid, liquid, gas. So if I'm going from solid, liquid to gas, do you think that's an endothermic or exothermic reaction? Why? It's a good guess. So this is going to absorb heat energy to break the bonds. So this direction is endothermic. So if I want to boil water, yes, boiling water is a hot thing to touch, but we needed to put heat energy into the water to get it to boil, thus making it endothermic. So some of it might be a little bit counterintuitive, because you might think boiling water is hot, it should be exothermic, but you have to think about the chemical reaction that's occurring. If I go backwards, that's exothermic. I need to take away heat energy. I need to get my molecules to slow down. Yeah. So when we freeze water to make ice, even though ice is cold, it's an exothermic reaction because we're removing heat from the water to make it freeze. That's why you put it in a freezer, to remove the heat. We okay with that so far? Okay, cool. So that's all I wanted to recap with this. So now what I can talk about is Hess's law. And I'll give you guys a past exam question so I can walk you through the calculations and explain how Hess's law works. Hess is a scientist that figured out that you can manipulate equations to figure out entropy. Yes. Let's talk about stuff. Okay. Ooh. Just occurred to me. Oh, actually, do I need to do it here? Or is the next question going to cover it? Oh, the next question will cover it. I'll do the next question. That's fine. Okay. Hess's law. Hopefully you guys won't find this one too bad. I don't think this calculation is too nasty in my opinion. All right. Hess's law works like this. So, ready? Okay. So do you see how we have all these chemical reactions? And each chemical reaction has a set enthalpy for it under standard conditions. So 1 atmosphere pressure, 25 degrees Celsius kind of thing. This delta H is talking about the enthalpy, so the heat change in a chemical reaction. You'll notice this year that they might have done it last year too, but you probably wouldn't have cared. There's these little letters in the subscript that gives us extra information. If it's just R, it's chemical reaction. But if we see an F or a C, I'll talk about what that means once we get to that question. So if you notice, I've been given 3 equations, and I know the enthalpy to all 3 of them. But this first equation up here, I do not know the enthalpy. What we can use is Hess's law, and Hess's law states it doesn't matter how I get to the end product. I can manipulate these equations, and if I manipulate these equations correctly and use their enthalpies, I will be able to figure out the unknown enthalpy of the reaction above. Client's giving me a face. Let me show you what we're doing, and then maybe it'll be better. All right, so there are 2 separate things that you can do when we're looking at a chemical equation. The first thing is we can flip it around, and the second thing is we can multiply it. We decide what we need to do based off of the original equation at the top. So what I'm looking for is basically I'm trying to replicate this equation at the top by adding these equations together. So if I look at my first one here, I see that I have the ammonia, and I see ammonia's up here. I see nitrogen and I see hydrogen. Now, those things aren't on the product side of this chemical reaction, and that's okay because I will cancel them out with Hess's law. What I notice here is that the ammonia is what side of the equation is it on? So we want to pay lots of attention to our arrows. And when we're doing our working, I would suggest line up your work so the arrows are in the center so you can easily see reactants and products. So here's my arrow. So I notice that the ammonia is on the same side as the equation that I want to get. Hello, ladies. So they're on the same side, so I don't need to flip anything around. The next thing I check, and hold on, I just want to get some quizzes. So, level 3 social studies is here to record you guys. So, are you going to pull them out one by one or in groups? Just do one of them at a time. They're fine. We're just doing notes. All right. Sorry, keep going. Okay. So, what I'm looking for is I want to check is the ammonia on the same side of the equation as what I'm trying to get up here. If it is, I don't need to flip it around. I just leave it as is. Okay. Here's my equations. That's 5? Yes. My keys. It's one of those days. All right. This poor video is going to have so many interruptions. I'm so sorry. Okay. It's what teaching's like. Okay. All right. So first thing I check, because I know Klein didn't quite get it, so we're going to go backtrack again. I look at this equation here. I look at this equation up here. I try to see, is there something in this equation that matches this top equation? And the answer is yes. It is that ammonia there. So I'm going to be able to manipulate this equation to help me solve this one. The next thing I look for is my arrow, and I look to see where is that ammonia. Are both ammonias on the product side? Are both on the reactant side? Is one on products and one on reactants? If they are on the same side, I don't need to flip the equation. If they are on opposite sides, I do need to flip this equation. So looking at this and this, these guys are on the same side, so I don't need to flip. The next thing I check is the ratios. So I see that this is a 2 and that's a 4. So I want the ratios to be the same. So I need to multiply this bottom equation by 2. Okay, so I'm going to start lining them up. So I like to put like I said, my arrow in the center. I'm going to multiply this whole thing by 2. So I would have 4NH3, and that's it on that side. And then I would have 2. Why am I having such a bad day today? And 2 and 6H2 as my first equation that I'm working with. You okay with that? Okay. The next thing I want to do is I want to keep track of my enthalpy. So in this case, I have taken my 92 and I'm multiplying it by 2, because again, it's the whole equation that gets multiplied. So I'm just going to keep a little tally on the bottom so that way I can add them all up. So I would have 92 times 2, and I'm going to keep it positive because I haven't flipped the equation around. So I'll keep the sign the same, the positive or the negative. So that's 184. So I'm just keeping a little tally at the bottom. Are we okay with that? Next one. All right. Let's look at my second equation here. So my second equation, again, let's pay attention to where the little arrow is. And let's see what is in this equation that's also in the top equation. So I see that there's water, H2O here, and I see we have H2O over here as well. I see that we have hydrogen, don't have hydrogen up there, and I see we have oxygen and we have oxygen. That's there as well. All right, so just trying to see what's going on in here. All right. I might actually do the next equation because this one I see that there's 2 things and there's 2 things up here. And I have 2 options with how I multiply it. I can multiply it by 3 or multiply it by 5. So I'm going to hold off on that one. I'm going to do the next one down. Do we understand my reasoning? No? All right. So 11. Okay. All right. So we see how there's 2 things in this equation that are in the top equation. I want to, again, match them up and, match them up. We see here how this is 2 and that's 6. So in theory, I should be multiplying by 3. This one here is 1 and that one's 5. In theory, we should be multiplying by 5. So I'm not sure, am I supposed to be multiplying by 5 or 3? So what I'm going to do is I'm going to skip this one and go back to it later. I'm going to do this one next to see if that one helps me figure out the ratios better. Yeah. There could be stuff on both sides and then it cancels out. Yeah, so that's what I'm saying. We're trying to manipulate it. We have 2 equations with oxygen. So what's going to happen when I do Hess's law is that the oxygen will add up together to the number I need. All right, so we're going to skip that one. We'll come back to it though, so don't worry. We are looking at the bottom one then. So for the bottom one, I can see that it also has oxygen and it has the nitrogen monoxide, that guy here too. Oh, bugger. They're both like that. Okay. Then I'll tell you my next way to figure it out. They have the same problem. I was hoping the other one wouldn't, but it does. That's okay. We're going to go back to the second one. All right. I can see with this one here, I have the same problem. This nitrogen monoxide is 2, that's 4, I should multiply by 2. This one's 1, that one's 5, I should multiply by 5. So now, since I've seen that kind of problem come up twice, that tells me, ooh, I should, go ahead, take them. I'll pause the video. All right. Gentlemen. Okay. What paper like this? This is thermal. Why are you giving yourself extra work? You're just like, ooh, it's math. I like math. I know. It's a shame you're not doing this one because it's actually really cool. Okay, so let's balance it, not in reference to the oxygen because I can see there's oxygen on 2 equations. So this should balance out to 5. What I'm going to do is I'm going to balance it based off the water and the nitrogen monoxide. Are we okay with that? Understood my reasoning? Say it again. All right. Since both of these equations have oxygen, they're going to add together, and that should make up 5. So I'm going to do my manipulations based off of the second item in these equations that I match. Because it's up there, it says 5. It's okay. All right. So with this equation, I see that the water is on the reactant side, but on this equation, it's on the product side. So I need to make sure I flip this equation, flip it around. And what else do I need to do? I see that this is 2 and that's 6. So I need to multiply by how many? 3. So we're going to do times 3 as well. So flipping the equation around, I would have 6H2 plus 3O2 and 6H2O. Okay. I also need to affect my enthalpy. So my enthalpy, you see how it's positive? Since I flipped it, I'm changing it to a negative number now. And I'm multiplying it by 3. So let's put that down at the bottom. I have 572 times 3. So I have a negative 1716. Happy? All right. Last equation is the following. All right. Okay. So, again, nitrogen monoxide. I look, it's on the product side. This guy's on the product side. So do I need to flip it? No. All right. This one's 2. That one's 4. What do I need to multiply this by? I'm going to multiply by 2. All right. So 2N2 plus 2O2 plus 4NO. And this one here, I multiplied by 2, so I don't want to do 180 times 2. 180 times 2, and that's going to be positive 360. For, yeah, 360. Okay, now let me show you. What we're going to do as our final step is we're going to add all these numbers together to figure out our enthalpy for this reaction. So I take 184 minus 1716 plus 360. And I get my enthalpy, delta H, is equal to negative 1,172. For thermo, it's really important we have 3 significant figures. It's just a weird thing. So if I was to do that, I would actually change it to 117. I'm going to round down to 0. And then my units is kilojoules per mole. That's my answer. Shall we double check that I made sure I did everything correctly? Can I move it? Do your organic. All right. I want to double check that I use Hess's law correctly. So I'm going to look at all these equations that I manipulated. And I want to make sure that things cancel out So I get the equation above. Okay? So NH3, I only have it on this side. No NH3 on this side. So I'm going to write 4 NH3. All right. Next thing I'm going to write or check, hydrogens. I have 6 hydrogens on this side. I have 6 hydrogens on my product side. So if I have it up both on my product and reactant side, they cancel out. That's good because that's not in my above equation. All right, not going to write that down. All right, next thing I see is oxygen. I have 3 here and I have 5 here. None on this side. So I'm going to write 5O2. And that matches with what I have up here. Okay? It's nice. It's a very like therapeutic thing, Hess's law. All right, N2. I have it on this side. I have it on the opposite side. Cancels out, which is what I want. That's good. That's why I'm saying you can double check yourself. It's idiot proof. All right. Last thing. These 2 have already been canceled out. H2O is not, so I'm going to use my H2O, which is up here, and also 6. I'm going to write the NO, which is also here, and 4. So I have the exact same equation that I have above. I have done my calculations correctly, and that's how Hess's law works. You guys want to see the marking schedule? Okay, let me show you. So this should hopefully be an easy excellence question. Yeah. What was I telling you? This is a nice question. This is probably the easiest question in thermo. This is the 2021. And this was question number 2. There you go. That's all the math. Got the same number. All right. Excellence. Correct answer, correct units with sign, plus the explanation for the bottom part. I'll talk about the explanation in the bottom. It's a very minor explanation, don't freak. All right. Merit point is correct process with 1 error. So you make the calculations and maybe you forgot to flip something or change the sign, or you multiplied something wrong, or you did a calculator error. That's going to drop you to a merit. Or if you forget your units, or if you forget your 3 sig figs. Pretty normal for chemistry. For the achieved is that you manipulated 1 equation correctly. So there are 3 equations that I gave you. Manipulate all 3 of them. So you have 3 chances for the achieved. You really don't know what you're doing, at least do that. Multiply it, flip things, whatever. Okay, let's talk about then the bottom part, which is explain why the standard enthalpy change calculated that you did in part 1 would be more exothermic if, now I'm trying to find another color that we haven't used. Are you guys done with the question? If you're done, you should go do the collated questions on No Brain Too Small, because these ones can get quite tricky. All right. So why is it more exothermic if I produce my water as a liquid instead of a gas? Anyone want to take a stab at that? Okay, the question here is, we see up here that the water is being produced in the gas state. If I was to produce this water in the liquid state instead, why would this chemical reaction release more energy? Think about the state changes. If I go from liquid to gas, do I need energy? Yes, I do. So if I go to liquid to gas, I need more energy to do that. So if I have this in the liquid state instead of the gas state, I would conserve some of my energy. Does that make sense? Because then I wouldn't be wasting my energy doing a state change. I could release that to the environment. Line, are we okay? Do you want me to repeat it? You don't know? Think so? Okay. Should I just move on? Okay. Brooklyn, you got it? No? Should I'm going to repeat it then. All right. Actually, you missed the beginning of the note, so yeah, this would make sense to you. All right. When I'm going, gentlemen, shh. Med school wannabes not doing work. No, I'm not going to be in med school. Okay. So, when I'm thinking about this, solid, liquid, gas, when I change states from a liquid to a gas, I need to absorb heat energy. If I go from gas to liquid, I release energy. So if this is in the liquid form instead of the gas form, I can conserve some of my energy because now I don't need to use that energy for a state change. I'm going to write it down and let you guys think about it. So evaporation from liquid to gas requires energy. End of. If this reaction produces water in the liquid state, it would conserve that energy. Therefore, more exothermic. Liquid state. It's going to conserve energy. Should I go back to the marking schedule just so you can see how the points broke down? Okay. So, looking at this point, basically it's the same thing I was saying. Enthalpy change would be more exothermic because heat energy would be released as the intermolecular forces form between the water molecules. It's the same thing in a different format. Okay, I see head nodding, that's a good sign. Achieved is recognizing that there is energy released when bonds are formed. So just some generic statement that you understand what endothermic and exothermic mean. Merit would be understanding that the energy is released as intermolecular forces are being formed for the water molecules in the gas liquid range. So just a little bit more of an explanation. If you have the correct calculation and the explanation, these two merit points convert to an excellence point. Okay? If you don't have enough excellence points to get like the E7 or the E8, then this will convert down as 2 merit points. So just FYI, they give you the better of whatever you're going to get. Okay? Cool. Questions, concerns, comments? All right. I've been mindful that I've been talking for half an hour and I don't want to talk for longer than that. There is another part to Hess's law that I want to show you, but do you guys want me just to put a pin in it? And you rather just do it now? Oh, wow. You want to do it now? Klein, do you want to do this now? Sure. Okay. Just mindful that I've talked for like half an hour. I don't want you guys to get burnt out. Okay. Okay. Here's our next question. Actually, you probably like this better because this is actually, I think, easier. Yeah, I would say it's easier. Okay. I would say it's easier. Less work. I just got to remember which way around it goes. Okay. So, What we need to now talk about is what this little F means and also what the little C means. So when I see something that is delta FH, like that, this is the enthalpy of formation. Formation, you're thinking about making something. Okay. Let's see what that one says. Oh, yeah, I can use it for this one. So there's actually an example of this on our exam question. It's on the back page for you guys. So we want to do the equation for the formation of glucose. So the way that the formation works is that we work. Gentlemen, you are so loud. I know. All right. The way the formation enthalpy works is we are going to work from the products backwards. So product-wise, I am making glucose, and I'm going to put glucose at the very end here so I have enough space. C6H12O6. And that is in the solid state. Yeah. What's important with the standard formation enthalpy is that the product, whatever we're forming, is set to 1 mole. I then use this to work backwards, and we make this compound from the pure elements. So I'd have carbon, and how much carbon would I need? 6. So I'd have 6 carbon in the solid state, plus the hydrogen in the in the molecule form, which is H2, because it's a gas. How many would I need? But I have H2, 6. And then oxygen is also a molecule, and it's got 2 of them. This has 6. This is 2. 3. And that's the formation equation. We good? Not too bad. All right. The other one that you're going to get is the combustion, which is burning. So delta CH is the enthalpy of combustion, which is burning. I'll write that note, set products to 1. Let me add some notes here so you guys have it. So with this one, be mindful that we are setting, ratios based off product formed being 1 mole. And then this side is going to be elements. So the elements make up our products. I'm just giving you some detail. I verbally said it, but I want to just write it down in case. Going back to the formation. So remember to set this to 1, and you're building it with the elements. Based off product formed being 1. Yeah. It's the same thing. We'll think about burning of glucose, burning sugar, which is down here. Ah, that's cool. All right, can I move it? Nope, not yet. Okay, ready to move it? Let's say I'm burning that sugar because that smells great. Okay, turn around. C6H12O6. Now, when we are talking about combustion, we're burning things in oxygen, so I always have oxygen on my reactant side, and then we have my products. So when I'm combusting things, I am breaking these guys apart to form whatever they form compound-wise with oxygen. So carbon pairing with oxygen forms carbon dioxide, CO2. And then hydrogen combining with with oxygen would form water. And this could be a liquid or a gas. I'm going to assume liquid. Yep. The states, yeah, they're going to matter this time. Yeah. Liquid. Just think about what you normally see things at when it comes to room temperature. Okay? Okay. So now what I need to do is balance the equation for the standard combustion of, for the enthalpy of standard combustion, for the combustion, the ratios are going to be set by whatever I'm burning. So whatever I'm burning needs to be at 1. Why is there music playing? Can you guys turn that off? So this is 1. Everything else is in reference to that one. Let's balance the oxygen last. Everything else can go first because the oxygen is going to be the most complicated. So carbon is 6 over here. So I need to put a 6 in front. Agreed? Agree, Klein? There's a 12 here. There's a 2 here. What number do I need to put in front? 6 again. All right. Now let's count my oxygen to figure out what number I need to put in front of here. So right now I have 12 and 6. So that gives me 18. Agreed? Okay. This side has 6 already. So if I do 18 minus 6, what do I get? 12. Okay. And then you see how that's O2? So I divide that by 2. So 6 goes there. And that's how I do combustion reactions. Yeah. Watch out. Just checking what time our class finishes. With these equations, don't freak out if you get fractions because that's probably going to happen at some point. So I don't think I have any examples in front of me, but if you get a fraction, because you have the ratio set to 1, you might get a half or like 3.5. Like that's fine. Okay? I know we normally don't want that, but in this case, it's fine. All right. What else did I want to say? They like to ask a theory question. How about we take a little break? I want you guys to do the equation for the formation of water. And I want you to do the equation for the combustion of hydrogen. Can you write those 2 equations down? Have a little break from me talking. All right. So this one, gentlemen, go pick another question off of the No Brain Too Small. You've gotten that one done. I know you. Don't lie to me. All right. The equation for the formation of water, start with H2O. Work your way backwards. I have hydrogen. I have oxygen. These 2 guys will be in gas. Oh, sorry. Okay. That's what you got? All right. Next one here, combustion of hydrogen. So in this case, you'd start with H2. You would be burning an oxygen. You'd be forming water. It doesn't really matter. You can write liquid, you can write gas. They're not going to be too fussed. Unless they state it somewhere in their equation that they want it in liquid form. Yeah. So one of the common questions they ask is, why is the enthalpy for the formation of water the same as the enthalpy for the combustion of hydrogen? The reason is they have the same equation. So the enthalpy will be the same. So don't get tricked up when they give you that question. You okay? All right. Last one, and I'm mindful of the time, so I'll just go over it with the marking schedule, is this equation here. So you see how they've done the combustion of the glucose. They've given you an enthalpy value, and they want you to figure out the standard formation energy of glucose. And they've given you that here. And then they've given you these two values, and they haven't given you the equation. You have two options with this. Option number one, and the long way of doing this, is you write out the equation for the formation of carbon dioxide and the formation of water, and you do the exact same thing that we did in the previous question. Manipulate the equations. Okay? That's option one. That's the long way. There is a shortcut, though, because what they have given you, both of these equations are in the formation form. So, important thing to kind of keep an eye on. Both of these are formation equations. So we can do a shortcut. All right, I'm just going to pull over to the marking schedule so you guys can see it, because we're running out of time. And I think this is question number 3. Here we go. Oh, that is a mess, but that's going to be okay. All right, so no, we're not looking at that one. We're looking at this one here. 309. Here we go. All right, so that was, oh, sorry, ran out of time. Go back to the other page. Yeah. I'll record the answer to this one. I'll put it online. I'll talk about this on Monday if I don't see you guys tomorrow. There you go. We can do a shortcut, and then I'll tell you what the shortcut is. Lesson. All right, finishing up this last question, because we did run out of time in class. I will cover this on Monday, if you don't quite get it. But in case those that wanted to watch the video and find out, you can find out how we got a little shortcut. So what we need to think about is, in this case, these two equations were given in the standard enthalpy of formation, and what we're trying to calculate as well is also in the standard enthalpy of formation. What this then means is I can then use a little shortcut and not have to do all the working that we saw in the previous Hess's law calculation. So what we need to keep in mind is that when we do the we can figure out the enthalpy if we have the combined total, so the sum of all of the enthalpy values of formation for the products minus the sum of all the formation energies of the reactants. That little shortcut. In this case, they've given it in a slightly different way than what you normally would have, because they've made this one the unknown, these ones the known, and then the enthalpy value, so this would equal to whatever reaction enthalpy that you're trying to get, as one of the variables they've given you. So what I know is my products are the carbon dioxide and the water. I can see them on this side of the equation here, carbon dioxide and water. So what I'm going to do is I'm going to put in the values for the products, and I'm going to still do the same equation manipulation. So in this equation, we do know with any of the formation, the products will be 1. So this compared to that is times 6, and then this compared to that is also times 6. So again, we're doing that same ratio matching, and I know these guys are already set to 1 because they are formation equations. So that is what I'm going to do. So you would do in this section here, negative 394 times 6, and you would do negative 286 times 6. And I'm just doing more brackets around so that way we can keep everybody together. When I'm doing the subtraction here, I'm subtracting from the formation of the products. This is actually my unknown because that's what it's asking for, the standard enthalpy of formation of glucose, and glucose is on the reactant side. So that's basically what I'm solving for. I can see that this is a 1 ratio, so I don't have to put any coefficient. We can treat it basically like x, our unknown. The other thing we have in our reactants is oxygen. Now, something to keep in mind with the formation of things is that the formation enthalpy is only referring to compounds. So if anything is an element, the number is 0. So I don't have to worry about anything else on this tail. I then set this equal to the enthalpy value of the reaction, so negative 2803. And basically then we just do the math. So 394 times 6, that's 2,364, and that's negative. Keep in mind the positive and negative signs. It does actually matter for this because it does refer to endothermic and exothermic. And also do show all your working, because if you make a calculator error, then we can figure out where that mistake went. And it might be something minor. It can make a difference basically between a merit and an achieved. You are not going to be getting an excellence if you make any minor errors, because that's the whole point of the excellence. All right, so that's done. In this case, I'm adding to get those to cancel out. Cool. And I get negative h equals positive 1277. I'm going to change the sign, obviously. So x is equal to 1277. So in this case, if I wanted to finalize my answer, it would be the standard formation of glucose is equal to positive 1, 2. Now be mindful, we are thinking 3 sig figs, so that's going to round up to 8. And then don't forget your units, kilojoules per mole. So that's the answer to that one there. Which, you had to write the equation and then give it to you. Okay. Just showing you the marking schedule again once it comes up. Yep, the right answer, which is good. And then this one only went up to the merit level because you can use that shortcut. So do keep in mind these ones aren't as much points. But correct answer, and this is kind of annoying that they do want the significant units and the the significant figures and the units for the merit, which is very unusual. Except 2 to 4. I don't know what that is referring to. Correct equation including symbol and states. So that's the first part that we were looking at. This one here is correct process with 1 minor error or an omission. So maybe you forgot somebody. But yeah, that is it.